We're going to finish up converting, and in this particular case, we're doing a conversion which would pretty much, it's effectively going to be on the test. It's a conversion using both a quantity that's cubed and a quantity that's not cubed. In this particular case, cubic meters per second. You could think of it as the amount of water coming out of a pipe. And I want to change it from 8 cubic meters per second to cubic feet per minute. And also, just no one's done anything wrong. I'm perfectly fine with people coming up and swiping while I'm speaking. If you think it's rude, I don't think it's rude. It initially caused me trauma, but it just blends in after a couple of years. Because I'd much rather have you swipe than send me an email after lecture going, I was there, but I didn't want to offend anybody. Just come on up. So 8 cubic meters per second. We need to convert this. There's no real set way of doing this. You could take the seconds first, 60 seconds per minute. Seconds go into minutes, and then minutes go, well, that's all we need to do. And then cubic meters, we have 100 centimeters per meter. We have 1 inch per 2.54 centimeters. And then we have 1 foot per 12 inches. Now, the one thing that you need to remember is that when you're using units that are cubed and squared, you've got to cube those conversions as well. So for the case of centimeters to meters, not an M, cube, inches to centimeters, cubed, feet to inches, and that's cubed as well. Now, I don't cube this because the 60 seconds and minutes are linear. Seconds, seconds, meters, meters, cubed, centimeters cubed, inches to inches, and I'm left with cubic feet per minute. So 8 times 60 times 100 cubed divided by 2.54 cubed times 12 cubed. And so 8 times 60 times 100 cubed divided by 2.54 cubed times 12 cubed. And I get, now this is kind of a little bit of philosophy. If I write exactly what is on the calculator, 16,951.04003. And this is in cubic feet per minute. Now, one of the things that we need to understand is in other classes, and with many, even with the physics professors, they place a big emphasis on sig figs, the number of numbers behind the dot. Now, in this particular case, I'm really more interested, my purpose as a Physics 213 instructor is to make sure you understand physics. And what I've found is that the professors and instructors who emphasize sig figs, what ends up happening is that the student becomes so just overwhelmed with making sure that they use the appropriate sig figs and the numbers, that they forget little things like understanding physics. So I do not place an emphasis on sig figs. We could leave that for another day. So an acceptable answer that I would find is just 16,951 cubic feet per minute. I really wouldn't have a problem with that. 1.70 times 10 to the 3 cubic feet per minute. I'd be fine with either one of those two. This would probably be the most accurate and the best way to communicate to the grader that you understand what's going on. This is just OCD over the top. Really, I don't need to know it to that many places. If you tell me that the answer is 16.2521876521, I'll be like, oh, just stop. Just give me like 3 digits most. And that'll be fine, because I will know if the answer's 2 and you give me 7,323.252, I know you've done something wrong. And so really the sig figs make no difference at that point. So this is a conversion problem. Something like this has been put into the problem set. Something like this will be on the test, and it will be the appetizer problem, just a simple 5-point problem. Should take you at tops 2 to 3 minutes. All right, so let's move on to something a little bit more interesting. So we've introduced units. We've introduced the scientific prefixes, the mega, the giga, etc. And now we're going to start doing things with it. Now, this is physics, this is not art class. So this is my image of the state of Mississippi. It's highly simplified. And then over here is Mobile, where my family lives. And there is Interstate 55, which goes from Memphis. And this is State Line. Now, granted, you notice that when you're driving along that you see mile markers. And so let's say, I understand it's not exactly this, but if you were to be at the Memphis line, it would be mile marker 300. If you were in Jackson, it would be 150. It's approximate. Let's just be flexible with this. I know that Oxford is not on I-55, but the exit, let's say, is 175. And then we've got State Line. And so with State Line, you've got mile marker 0. And you notice that in all interstates, for the mile markers, the southernmost point is the 0 mile marker, and it goes further up the more north you get. I forget, it counts down if you're going from east to west, I think. The last class that I gave, and I did this example, I said, so you're right at State Line. I can't say this joke like a year or two from now because people will forget. And I said, what mile marker do you see when you're on the state line from Mississippi to Louisiana? And they said, less miles. And I was like, genius, that's just, I never thought of that. But state line is what we think of as an origin. You have to have a place where you go, everything is based on its relationship to that. We could pick you as the origin, and we could figure out everybody's position relative to you or relative to me. You can only have one origin. You can only have one point as the center. If you have two, then things just get crazy. So we have the idea of position, which is just the mile marker, and we give it a letter and we call it X. Typically, when you're dealing with one-dimensional motion, the letter that you use is X. For those of you who are moving on to biomechanics later, they're going to change all the letters on you. In physics, physics grew in many different locations, Europe, Asia, Australia, all sorts of places. And depending on where you're from, you use a different set of letters. As physicists, you need to just accept this fact. And in one case, I use an X, you use a Y, but as long as we define what it is, instead of saying the coordinate is X, you could say the coordinate is cheeseburger, as long as you say what it is. So the position is the mile marker X. If I said your X is 275, you're close to Memphis. If I say it's 3, you're close to state line. If it's 178, you're close to town. And then, this is for one person, but let's say you were in one town and then went to the other town. There's the concept of displacement, change in potential, or change in position. And this displacement is known as delta x. X being the coordinate that we're using, or the variable that we're using. Delta meaning this is a delta, and it implies change. And more importantly, macro change. Displacement is this equation right here. If you were, let's do this as a problem. If you were in Oxford and drove to Jackson, what is your displacement? What was your change in position? Your net change. So delta x is x2 minus x1. 1, your initial position. 2 being your final position. Now, in this system, once again, talking about how other people do certain things, and as long as you define what it is, I will make an attempt to use the 2 as the final position, as 1 as the initial position. But there are other systems. Sometimes you get I or xi and xf. The initial position x, the final position x. Other times they use x0 and x1. x0 being the 0th position. Other times you can think of it as the original position. So there are different ways of doing this. I typically use this. The one thing that I would ask is don't mix it up. Don't have an xi and an x1 unless you really write down what these things mean. Try to be consistent with the system that you've chosen. I don't mind either one. But once you pick a system for a problem, you need to stick with it. So for this displacement, your final position is 150. Your initial position is 175. So your displacement is negative 25 miles. Now notice also, just as a tip, when you give your final answer, final answers must include your units. During the problem, I don't particularly care. And I don't use units in the middle of problems because it's just a waste of time in my estimation. But you can if it makes you feel comfortable. Displacement can be positive or negative. So you could go, when you go from Oxford to Jackson, it'll be a negative displacement. When you go from Jackson to Oxford, you have a positive displacement. The positive and negative sign gives you information on the motion. In this, the way that it's set up, positive displacement means north. Negative displacement means south. Now there's another definition, distance. And some people use S, some people use D. I'll just use little d. Is the absolute value of displacement. So little d is just absolute value of delta x. And so absolute value of negative 25 or 25 miles. So whereas displacement can be positive or negative, distance distance is always positive. So if I say the distance is negative 3 miles, you know that there's an issue. If I say the displacement is negative 3, that's allowed. Positive 3 is allowed. But the distance is always positive. It's the magnitude of the displacement. And really on this first day, we're kind of doing an info dump of all these words. Now, and one thing I will say, this particular sketch, there is a problem in the problem set that you have to use this sketch. So just, I know how complex it is, but just be sure you got a copy. Now, two new words. Velocity, and in this case we're going to discuss average velocity. Average velocity is the displacement divided by the time. So if it took, well, let's do the example. You went from Oxford. Did I really put 175 in that? Okay. Should have been 225, but oh well. Oxford to Jackson in, let's just say 2 hours. What is your average velocity? And average velocity, the symbol that we use is V with a bar. The bar says that we are dealing with an average. So if it took 2 hours and the displacement was negative 25, the average velocity is the change in position with the change in time, which is negative 25 over 2, or negative 12.5 miles per hour. So the velocity is in the negative direction. It can be positive or negative. And then the second word that we need to know is average speed. And that is merely, I just use S in this case, with the bar, since we're dealing with average. And that is the absolute value of average velocity. So the speed in this case is positive 12.5 miles per hour. And so that is the difference between average speed. So we have the concept of position, change in position or displacement, change in position with respect to time or velocity, and then their absolute values. And so as one of the demonstrations that no one has ever accepted to do for me, and so this is one of the first questions that I have for the class, is I need you to get your car, find a cop, put your car in reverse. Probably on Highway 6, that's probably the best place to do it. And just gun it. Go as fast as you can. And then have the cop pull you over, and just pull over. And they go, well, you were breaking the speed limit. I caught you doing 70 in a 55. And then you say, no, officer, I was doing negative 70 miles an hour because my car was in reverse. What's wrong with this logic? It's velocity. And actually, you need to speak up. Phil, you can say it louder.
It's velocity.
It's velocity. So the velocity was negative 7, but his 70, but his speed was 70 miles per hour. Good. Also, I tweeted OPD with that question, and they also said, well, that's reckless driving and a few other things. And I was like, well, okay, point taken. So know the difference between speed and velocity. In fact, when we start dealing with more complex topics, we have the idea of instantaneous velocity and instantaneous speed. The instantaneous speed and the instantaneous velocity don't have the bars on top. And instead of using the deltas, you use the little x, or I'm sorry, the little d's. And what the instantaneous velocity is, and its difference from the average velocity, the instantaneous velocity, if I'm just walking across the floor, boom, that point, I would have a particular velocity. Now, if I'm doing something like this, so did I have an average velocity? I did. I had a particular distance, I had a particular time. You take the total distance, divide it by the total time, boom. Did I have a consistent instantaneous velocity? No, it changed throughout the motion. So there is a difference. There's an example problem you're driving to Walmart, we all know what West Jackson's like. Your velocity or speed down West Jackson is almost never consistent. You speed up, you slow down, you come to a stop, you accelerate forward, all that stuff. But you do have an average velocity. Take the total time divided by the distance. We will be mainly dealing with instantaneous velocity, and pretty much from now on, we're just going to call it velocity. The displacement and average velocity and all that stuff we use initially, and then we kind of move on to other things. But instantaneous velocity is what we use on a regular basis. Now there is the idea of average acceleration, which is just the change in velocity with respect to time. It's not used in 213. What we do use is instantaneous acceleration. And that A is dv dt, the change in velocity with respect to time. As I was accelerating across the floor, at the beginning I had a low velocity. At the far end of the room I had a higher velocity. The velocity was changing, and it implies that there is an acceleration. In 213, acceleration will be a constant. I know there are problems in the book, and they're real problems, where a car accelerates to a particular velocity and then it coasts for a couple of minutes, and then it comes and then it puts the brakes on and it slows down. In 213, we're trying to deal with the big picture. I'm not going to really focus on problems like that. In 213, acceleration will be a constant. It will be 0 and always 0, or some non-zero value and always that value. Now, if I had a lot more time with you, if this was like a 6-unit class where we'd spend like, oh joy, like 6 hours a week together in lecture, yeah, then we'd go over the smaller details. But in terms of this class, since I know I'm dealing with people who have taken physics for the first, how long have you been taking physics? Well, for about 3 days now. I know you guys are just getting started, so we're keeping things simple. Acceleration. Burn this into your brain as far as I'm concerned for 213. It will always be 0 and never change during the problem. But what do you mean never change? I mean never change. So if it's 0 now, what is it going to be 5 days from now? 0. Exactly. How hard is that? If it's negative 2.2 here in America, what is it in France? Negative 2.2. Regardless of location, regardless of time, that acceleration is always going to be the same. I say this repeatedly because I'm going to trip someone up major league bad in front of everybody, either today or Tuesday. So be prepared. As long as you remember what I have just said, everything will be fine. No embarrassment on your part. It'll be awesome. All right. Now, acceleration is as far as we go with regards to change in position with respect to time, velocity. Change with velocity with respect to time, that is acceleration. But just as a way of going, well, what is the change? What is the change in acceleration with respect to time? There is a value for that, and that is called the jerk. That there are situations where the acceleration will be 0 and then change with respect to time. And we call it J. So J is dA dt. Which then begs the question, well, what's dJ dt? Well, that's called S. I'll get to that. I'll get to the real name in just a moment. And then ds dt is called C. And I'm not making this up. People thought this is a joke. dc dt. So the change in position with respect to time is velocity. Change in velocity with respect to time is acceleration. Change in acceleration with respect to time is jerk. And then change in jerk, snap, crackle, and pop. In America, it's called snap, crackle, and pop. In Europe, Europeans are not funny, and so they use 3 other words, but we won't use them. But jerk, I believe, is consistent between the 2 systems. And then there's snap, crackle, and pop. This won't be on the test, but at least now you know. So there we go with all this stuff. Now, one of the things that let me go back. When I talk about X and position, it has the units of meters. When we have tests, when we have problems, if you need to give an answer in the form of a length, you will never be wrong with using meters as a distance, displacement, stuff like that. For delta X, again, is in meters. For velocity, instant velocity, it is meters per second. And acceleration, meters per second per second. Knowing your units will give you confidence when solving problems. I am a big fan of unit checks. As an example, let's say, what is the equation for average velocity? Average velocity is capital V. Capital V is delta x over delta t. Delta x is x2 minus x1 over t2 minus t1. Now for the units, x2 is in meters, x1 is in meters. What happens when you take meters and subtract meters from it? You get more meters. So that is in meters. Time minus time, seconds minus seconds, you will always get seconds. So the equation does check out. You know that velocity, an average velocity, should have units of meters per second. We got meters in the numerator, we got meters in the denominator, we're good to go. This is obviously a trivial problem to double check, but when you're doing far more complex equations, if you do a unit check and you're supposed to get velocity, and it looks like you, or some kid ate a can of alphabet soup and just spewed it all over the paper. And if you do all the units and it comes out to be meters per second when you're expecting a velocity, then you know you're on the right path. Okay, so with these types of situations, what we're really doing is we're building towards one-dimensional motion. And now that I'm thinking about what you guys are doing, I'm going to pause this lecture for just, not pause it, but stop talking about this. What I try to do, now that I'm reminded of it, is basically go over the lab. On Tuesday, we worked with vernier calipers. On Monday, the TA told you about how to use it. And this Monday, the Monday of next week, we're going to use it in the measurement lab. And what you're going to do is, the big part of this experiment is, given an assortment of cylinders, collect data and analyze. So let's talk about what happened. So you're given just a whole wide assortment of cylinders. And what you do is you wrap a string around the cylinder one time. And what value do you get when you take a string and you wrap it around the cylinder just once? Circumference. And with the string, you're not using your vernier caliper. You're just going to use like just a ruler. And then you're going to use the caliper to measure the diameter. So you get the caliper and you measure the diameter, you get string and you get circumferences, and what's going to happen is you're going to build a table of circumferences and diameters, and you're going to get a table, and you're going to write all those numbers down. And what you're going to do is you're going to find out that when you plot your data, that you're going to get a line, and you're going to learn how to fit lines and use plotting software, and that's going to be one of the things that you do on Monday. And all of this is so that you understand that circumference is what? 2 pi r. And what is 2r? The diameter. And when you look at this equation, given a diameter, you get a circumference. The circumference will be on the vertical. The horizontal will be the diameter. And this has, you've seen the linear equation, y equals mx. The x coordinate is your independent variable, your diameter. Your y coordinate is your dependent variable. And what you do is you plot it out, and then the slope should be pi. The slope of that line should be 3.14. Now, if you plot it the other way, if you plot it diameter on the vertical and circumference on the horizontal, then the slope will be 1 over pi. So whatever 1 over, roughly 1/3. But if you plot circumference on the vertical and horizontal as diameter, you got it. And that is the first lab. There are a few other things, but this is the big deal. All right. It's really just to get you in the lab, get you start messing with some equipment, and most importantly, start working with the fitting software. So now back to one-dimensional motion. In one-dimensional motion, it's really, in some cases it's a hardship, in other cases it's a little bit of a freedom. If I was teaching Cal-based physics, oh, the fun that we would have, because we would be able to derive so many things, but this is algebra-based. Algebra-based means I'm not allowed to use calculus. I'll occasionally dabble in it, and then it'll frighten you, and then I'll stop. But so the downside on my part is I can't use calculus. The upside on your part is you don't have to use calculus. But there is a little bit of a downside because a lot of the questions that students ask of me is, why is it this way? Why are the equations working out this way? And the only way I can say it is because I say so. It has to be done that way because the only way that I could truly do it is to just start doing calculus in front of you, and then you'd pass out, and then it wouldn't be any fun. So these equations for one-dimensional motion, x equals x naught plus v naught t plus 1/2 a t squared, and v equals v naught plus a t. This is the equation of motion for position. This is the equation of motion for velocity. So given a set of circumstances, you can work with an object's position and velocity using all sorts of things. Now, the x is position. X naught is the initial position. What we used is x1 when we were dealing with displacement. V is velocity. V naught is initial velocity. T is time. And then A is acceleration. X is position, x naught is initial position. Both of those units are in meters. Velocity and initial velocity, those are in meters per second. Time, obviously, is in seconds. Acceleration is in meters per second squared, or meters per second per second. So those are the units that you use for these equations. In Eschenberg Physics 213 slang, This is Dr. Eschenberg's favorite equation. This is Dr. Eschenberg's second favorite equation. When you are working with one-dimensional motion, when you're working with two-dimensional motion, for the next couple of weeks, in fact, throughout, for those of you who are going to take 214, these two equations will help you work with any problem in one-dimensional motion or in two-dimensional motion. We'll get to that in a little bit later. In the book, there is a list of, I think it's a list of 5 equations, and they show this one, and 3 other equations. Ignore those other 3. They are not allowed. They are, if you derive them from these 2, then have fun, do whatever. But what I am trying to do is appeal to your sense of laziness, or as I like to say, efficiency. Why memorize? What's harder? Or let me say this. What's easier, memorizing 2 equations or memorizing 5? I want to memorize 2. So why bother with those other 3 when you can get those other 3 quite easily? So these 2 need to become your new best friends. So let's look at these equations in a little bit of, in more detail. And what we're really doing now is we're thinking about stuff that's going to go on in not next week's lab, but the week after that. X equals x naught plus v naught t plus 1/2 at squared. This is a quadratic equation. Quadratic equations, you can tell because in this particular case, most plots, they use time as the independent variable. In this one, there's no t. In this one, there is 1 t. And in this one, there are 2 t's. And we write it as a t squared. It's quadratic. And so the shapes are curved. So it could look something like this. It could look like something like that. But as you can see, the slope of these lines are changing. This, the v equals v naught at, it's a linear equation. So its form, it could go like this, it could go like that, it could go like that. As long as it is a line, hence linear equation. So what we're going to do is, I'm going to be the demo, and what we're going to do is we're going to plot several actions on all of the horizontal lines. They're all time. In this column, they're all the verticals are all X's for position. Here, they're velocity. Here, they are acceleration. So all the times. So the first one is going to be easy, but the real first thing that we got to figure out is I'm going to take this water bottle and I'm going to declare it to be the origin. So if I am right here, I have a coordinate of 0. Now we also have to gain an idea of, well, what's the difference between coordinates that are over here and coordinates over here? In the problem with the state of Mississippi, everything was on one side of state line, or the water line. So what we have to do is introduce the idea of there can be negative coordinates. So if I'm to the left, I have a negative coordinate. If I am to the right, I have a positive coordinate. So now, the first thing I'm going to do, it's about to start. Y'all watch carefully. I'm doing now, begin. Okay, I'm done. So that was the first demonstration. What was the value of my coordinate?
Negative.
It was negative. So just some negative value. At the beginning, it was that negative value. Let's say -2. Throughout the entire motion, did it change from -2? No, it was always 2. So when we write it and plot it, it has a value that's negative, and that value remains consistent. So it's like at one point in time, I'm there. In the next point in time, I'm still there, etc. Now, what does my velocity look like? So at the beginning of the motion, I'm not moving. In the middle of the motion, I'm not moving. At the end of the motion, I'm still not moving. So did I have a velocity? Well, technically, yes, 0. 0 was that value. So when you plot this out, it's consistent, constant, and the value 0. Now let me ask this question. What was my acceleration during the motion? It was 0 throughout the entire motion. Remember what I've said, constant and 0 is an acceptable answer. So that acceleration is like this. So this is for standing still. Now, we'll do the next experiment. And really what I'm doing is I'm working through, I think with the labs, you guys need to start doing pre-labs, which is just basically, did you read the basic material? Did you go to class? Because effectively, I'm doing the lab right in front of you. There is a page where you have to fill out all these forms like this, just to show the curves and how they look like. So the next motion, I gotta get started for this, is simply this. Now, that's done. So what did I do? What was my position at the beginning? It was positive. At the end, it was what? Negative. So we kind of know that it started out about here. It ended about there. What did my velocity look like? It was constant and negative. How could you tell that the velocity was constant? Because I didn't change velocity. It didn't change speed. How did you know that my velocity was negative? because I was heading that way. Let me ask you another question. I'm on the positive side. How can I have a negative velocity? Because it doesn't matter what position is. What matters with velocity is where you're headed. So you can be on the positive side. If you're heading in the negative direction, then you've got a negative velocity. So during this particular moment, or throughout the motion, that velocity was negative and constant. A negative constant velocity implies that that position doesn't really curve. It's a linear line. Now let me ask you about acceleration. Was there an acceleration in the motion? No. Give me the definition for acceleration. Change in velocity. He just saved it. So the velocity doesn't change. The slope of that flat line is what? 0. So if that line is flat like that, that has no slope. M is 0. If that line was at an angle, acceleration would have a value. So acceleration is like this. I'm only drawing it slightly off just to show you that the line is there. So let's first take a look at that line. That line has a positive or negative slope? Negative. Is it 0? No, it's a negative non-zero number. So that number, the slope of this line is the value of that line. And the slope of this line is the value of that line. So constant slope means one value of velocity. No slope on velocity means that in addition to the slope of the acceleration being 0, and slope of acceleration will always be 0 in this class, the value is also 0. So begin to associate motions with its position, velocity, and acceleration and how they behave, because they're not consistent. Well, they're not consistent with each other. What's the big difference between this and that? The slope of that line is 0, so you get this. So comparing this to this is the same as comparing that to that. Because this has no slope, that has no value. That has no slope, that has no value. That has a constant negative value, so you get a flat line for a negative value. And so just start thinking about it. Next motion. So I'm going to do this. Hopefully I won't just bash my head against the wall. So begin. Stop. So that was the motion. Did I have an acceleration? Yes, I accelerated. Now, it was a constant acceleration. Was the acceleration positive or negative? Positive. Why? I was heading in that direction. The velocity was increasing in that direction, so the acceleration has to be in that direction. So the acceleration looks like this. What was my initial velocity? 0. I was standing still at the beginning. And then it started creeping up faster and faster. The velocity was increasing at a steady rate. So the velocity started at 0 and became positive. Now, one of the things that would be wrong, if I started here, someone should go, whoa, 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 wait. You weren't moving initially. Don't start at that point. You started with no velocity, so you start here. Where did I start the motion? On the negative side. I did not start it at the origin. So for the position equation, it looks like this. It bows upwards. The slope of this line was very low at the beginning because the velocity was nothing. With time, the velocity increased, so the change in position increased as well. All right, now, this is one of the big questions, or big motions. It's probably the one that I'll die in. So, we'll do this. Like that. Now, granted, it wasn't exactly, but let's just play with it. So what was my motion from the perspective of position? I started at the negative, I ended up positive, and then I came back negative. So I arced up, or arced to the right, stopped, and came back. So it looked like this. So initially I had a very high velocity in the positive side. Then it slowed down, became 0, and then started going back in the other direction. So what does my velocity look like? So initially it had a very high slope, a very positive slope. So it started here because the slope was going up. On the other side, slope going down. So it looked like this. So the velocity had or has a slope in the negative direction. So what does the acceleration line look like? It's in the negative. So it looks like, and it's flat, because it has a constant slope. And so there it is. Now here's the big question. This is similar to just throwing a ball up in the air. Ball throws up in the air, comes to a stop, then it comes back down. Much as like I started running over here, coming to a stop, then running back. Who do I know everybody's looking away. You, I think you're the one who saved the other guy. Don't look at that eyeball. What's the acceleration of the object when it came to a stop? Excellent. I won't have to kill you. Do we understand what went on? Acceleration is different from velocity. Throughout the motion, as I was slowing down, my acceleration was backwards. As I was coming back, my acceleration was still backwards. So there are occasions where you can have a positive velocity and a negative acceleration, much like throwing a ball up in the air. As it's going up, its velocity is positive, but its acceleration is negative. As it's coming down, its velocity is negative, and its acceleration is still negative. And at that very top part, the acceleration